Welcome to Thermal Intelligence, brought to you by ThermoNeural. This is where artificial intelligence meets thermal engineering. Each week, we explore how AI is revolutionizing HVAC systems, data centers, and building energy management, from cryogenic precision to everyday comfort. Today's episode: how quantum computing's extreme cooling is reshaping the future of HVAC technology. The refrigeration breakthroughs happening in quantum labs today are the energy efficiency innovations we'll use in buildings tomorrow. Let's dive in. So here's the challenge we're facing in the thermal engineering world, and it's coming from a place you might not expect. Quantum computers need to operate at temperatures colder than outer space. We're talking about 10 millikelvin, that's negative 459 degrees Fahrenheit, or just 1/100th of a degree above absolute zero. Now you might be thinking, what does quantum computing have to do with HVAC? Here's the connection. The dilution refrigerators that make these extreme temperatures possible represent the cutting edge of thermal management. And the global market for these ultra-low temperature systems is projected to grow from about $73 million in 2024 to $193 million by 2031. That's a 15% annual growth rate. This isn't just lab equipment anymore. Companies like IBM, Google, and Microsoft are racing to build commercial quantum computers. And every single one needs a dilution refrigerator that costs 25 kilowatts of continuous power to operate. Here's why this matters to you as an HVAC professional. These systems are solving the same fundamental problem you deal with every day: removing heat efficiently. The difference is scale and precision. While you're managing comfort in buildings, quantum engineers are fighting to remove every last fraction of a watt of heat to keep qubits stable. And the lessons they're learning about thermal management, refrigerant efficiency, and heat exchanger design are already trickling down to commercial HVAC applications. Now here's where things get interesting. There are two main types of dilution refrigerators, and understanding them helps explain where commercial refrigeration is headed. First, you've got cryogen-free or dry systems. These use mechanical pulse tube coolers, similar in principle to the compressor in your RTU, but operating in stages to progressively lower temperature. They start at room temperature and cascade down through multiple cooling stages: 50 Kelvin, then 4 Kelvin, and finally down to those 10 millikelvin temperatures. The challenge? These mechanical coolers create vibration, which is the enemy of precision measurements. Second, there are wet systems that use liquid helium. These are completely still, no vibration whatsoever, making them perfect for the most sensitive applications like scanning, tunneling, microscopy. But they require constant refills of helium-3, which is becoming increasingly scarce and expensive. Think of it like this. It's the same trade-off you make when choosing between a standard scroll compressor and a variable speed inverter system. One is simple and robust. The other is more complex, but delivers better performance when you need precision control. Here's the breakthrough. Companies like Bluefors and Oxford Instruments have engineered these systems to achieve cooling power of 500 microwatts at 100 millikelvin. To put that in perspective, that's like removing the heat from a single grain of rice, but doing it at temperatures where normal physics doesn't apply. The magic happens in what's called the mixing chamber heat exchanger. They're using sintered silver powder with specific surface areas of 3.56 square meters per gram to maximize heat transfer at these insane temperatures. That's like having an evaporator coil, where every single molecule of metal is exposed to refrigerant. Let's look at actual numbers from real deployments, because this isn't just theory, it's a booming industry. The dilution refrigerator market was valued at $200 million in 2023 and is forecasted to reach $450 million by 2032. That's more than doubling in less than a decade. But here's what's really telling. Cooling dominates the overall power usage in quantum computers, a complete reversal from classical data centers where cooling is only 2 to 20% of power usage. A single dilution refrigerator running a quantum processor consumes about 25 kilowatts continuously, and the cooling accounts for 50 to 70% of the total system cost. That's equivalent to running 25 high-powered air conditioners 24/7, just to keep a device the size of a coffee can cold enough to function. Now let's talk about what's happening in the supply chain. China achieved 8 millikelvin on a domestically developed system back in 2021, breaking dependence on Western suppliers. Japan's HVAC is partnering with IBM to build local manufacturing capacity. And Canadian startup 0 Point Cryogenics just received a US patent for a new phase separation refrigerator that achieves 500 millikelvin continuously without requiring massive amounts of helium-3. What this proves is that extreme cooling technology is no longer confined to physics labs. It's becoming industrialized, competitive, and increasingly efficient, which means the innovations are ready to transfer to commercial applications. So what does this mean for you as a contractor, technician, or building engineer? Here are 3 actionable takeaways. First, quantum computing research is already improving HVAC control systems. Researchers at Hanbat National University in South Korea used quantum reinforcement learning to control residential HVAC systems and achieved 63% reductions in power consumption while maintaining thermal comfort. The same computational methods that optimize qubit cooling are being applied to multi-zone building systems. This technology is retrofit-friendly and works with standard sensors and equipment you're already using. Second, watch the cryogenic cooling supply chain for component innovations. Companies like Bluefors now offer dilution refrigerators with cool-down times under 12 hours, down from days just a few years ago. Their heat exchanger designs are being adapted for high-efficiency commercial refrigeration. The next 2 to 3 years will see these advanced heat transfer technologies appear in premium HVAC equipment as patents expire and manufacturing scales up. Third, energy efficiency innovations are transferring from quantum to commercial. Google's quantum team has a roadmap to reduce cooling power needs by 50% through better refrigeration. Those same techniques, improved insulation, cascade cooling, and precision temperature control, are already appearing in variable refrigerant flow systems and data center cooling. As quantum computers scale from hundreds to millions of qubits, the cooling efficiency improvements will accelerate, and those breakthroughs directly benefit the HVAC industry. The bottom line, the extreme cooling demands of quantum computing are forcing engineers to rethink fundamental refrigeration principles. Those innovations, better heat exchangers, more efficient cascade systems, and AI-powered control, will become standard in commercial HVAC within the next decade. Looking ahead, we're seeing 3 major trends that connect quantum cooling to everyday HVAC. First, quantum computing applications for building energy management are moving from research to reality. Studies show that quantum-enhanced model predictive control for HVAC systems can reduce computation time from hours to seconds, while achieving solutions within 2% of traditional optimization methods. That means faster, smarter building control, with 80% reductions in peak energy consumption when paired with demand response programs. Second, the push for more efficient quantum cooling is driving heat pump innovation. Photonic quantum computers that operate at room temperature are in development, and if successful, they'll eliminate the need for extreme cooling entirely. That research is accelerating development of ultra-efficient heat pumps for buildings. Third, we're entering an era of intelligent, adaptive cooling systems. The same AI algorithms that manage thermal noise in quantum processors are being deployed to predict and respond to building loads in real time, accounting for occupancy, weather, and grid signals simultaneously. The global quantum computing market is projected to grow from $1.2 billion in 2024 to $12.6 billion by 2032. Every dollar spent on quantum research includes significant investment in better cooling technology, and those advances benefit the entire thermal engineering industry. We've covered how quantum computing's race to absolute zero is driving breakthrough innovations in refrigeration technology, heat exchanger design, and AI-powered thermal control, all of which are already improving commercial HVAC systems. Want to start applying these concepts? Check out the ThermoNeural calculator at thermoneural.com. We've got professional HVAC templates and tools to help you optimize thermal systems with AI-powered precision. This has been Thermal Intelligence from ThermoNeural. Smarter thermal systems through neural intelligence. Thanks for listening.